Okay, this is NEAP 2015, Maths Methods Exam 1. We're going to do 2 or 3 questions out of this exam. The first is question 3, which is worth 4 marks. And the first part is to solve 2 sine 2x minus pi and 6 equals root 3 in this particular domain. So the first thing we'll do is write down the expression and then divide both sides by 2 to get root 3 on 2, and then realise that we've got this particular domain here, so really we need to adjust the domain. We're given that x is between minus pi and pi, so we can multiply by 2 to get 2 pi and minus 2 pi, then subtract by pi and 6 to get 2 pi minus pi and 6, and minus 2 pi minus pi and 6, which is really minus 13 pi and 6 and 11 pi and 6. What does that mean exactly? Well, to find out, we go to the unit circle, and 11 pi and 6 is really around the unit circle to 2 pi and 6 and a little bit back pi and 6, which gives us 11 pi and 6. We also have the other part of the domain, which is minus 13 pi and 6. So if we go the other way, so if we start at 0 and go around to minus 2 pi, a little bit more, pi and 6 more, we also get to this line, which is minus 13 pi and 6. So what exactly does that mean? In terms of our solution, we need to find out what sine of the inverse sine of root 3 on 2 is, and we use this triangle here. So the inverse sine of root 3 on 2 is going to be pi and 3. So the basic angle is pi and 3, or the base angle. And we can locate that on the unit circle. There it is. But that's not the only solution that we would have. We would also have a solution if we go around the unit circle. We've got pi and 3, and then we've got probably another solution here where sine would be positive root 3 on 2, and that would be 2 pi and 3. So again, going around the unit circle, if we start at 0, go around, we've got one solution at pi and 3, another solution at 2 pi and 3, we keep going around, we've got to stop at 11 pi and 6 because that's the end of our domain. So we start with these 2 solutions, pi and 3 and 2 pi and 3. But of course our domain is not just to 11 pi and 6 going anti-clockwise. We can also go clockwise to get some solutions. So let's do that. So going clockwise, we're going to go around this way, and we see that we've got a solution at this point, and then it stops at minus 13 pi and 6. But that's not 2 pi and 3 there, it's going clockwise around the unit circle, and that would be minus 4 pi and 3 and minus 5 pi and 3. So they're also solutions to this expression. So all we need to do now is add pi and 6 to both sides and divide by 2 to get our solutions for x. So there we are, adding pi and 6 to each of those solutions, cleaning them up a bit, and getting our solutions with a denominator of 12, and again 3 pi and 12 can be written as pi and 4. So there's the solution to 3a. Let's go to b. So in 3b we've got a graph that we've got to sketch, and it's the same function as we had to find the solutions for, which is kind of handy because the solutions that we found are actually the x-intercepts. So we can put those on the graph almost straight away. Now I've got a little change here in that instead of calling it showing all axial intercepts, I've written it as labelling the coordinates of. It's probably a good idea to label things as coordinates. So I'm going to do that straight away with my x coordinates. So instead of just putting pi and 4 there, it's pi and 4 0, 5 pi and 12 0, minus 7 pi and 12 0, and minus 3 pi and 4 0. So that's where we could start. The next place that we really need to think about is to rewrite the expression in this way. So if we rewrite this with our brackets, and we do this because we want to find out the period and, more importantly, the horizontal translation, which is pi on 12 to the right. It's not actually pi on 6 to the right. We need to be careful about that. So we have a period of 2 pi over 2. That's 2 pi over this 2. That gives us pi. We have a period of pi, which means that in this graph we're going to have some shape, but its cycle is only going to last for pi units. And we see there that we've got pi there, so we're really only going to get one cycle in this half of the graph, and maybe one cycle in this half of the graph as well. So let's go to our maximum minimums. So our maximum is going to be our average value. We get that from our equation, minus root 3, plus our amplitude, plus the amplitude 2. And we get roughly 0.8. Now, I'll put that in there only because that's going to make it easier to sketch on the graph in a minute. We get our minimum much the same way, minus root 3, minus root 2, minus the amplitude, we get about minus 3.2. So now we've got our guidelines, so our maximum is not going to be any greater than this, and our minimums are not going to be any less than that. We're kind of getting an idea already for how this graph might look. Next thing we do is find the y-intercept. That's just by making this x value here 0. So this will become either here or in our function just there, making that x 0, and we get sine of minus pi on 6, which is negative a half, times 2 minus 1. So our y-intercept is going to be 0 minus 1 minus root 3, which again I've written as coordinates. And the next thing we need to do is find the endpoints. So we'll start with the endpoint at pi. So since pi is the endpoint of our domain, it's given up here, that means we'll substitute pi into the equation. We get 2 pi minus pi on 6, which is 11 pi on 6. That also gives us minus 1 minus root 3. So we'll just put that into our graph as a point, and we do the same for minus pi. So we substitute minus pi, we get minus 2 pi minus pi on 6, and that also gives us minus 1 minus root 3, put in the point. And we can really see from this graph now, it's pretty straightforward how it's going to go. We know that it's going to go over here and then back around here, over there, back around here, and we're just not sure where the maximums or minimums are, but you can see symmetrically that it's going to look a bit like this and then like that. We're not asked in this question to find the maximum points there and the minimum, but you can use the grid. Using the grid is a really good idea, and I didn't talk about that before, but I think I will now, particularly in terms of the maximums and minimums. These values like 5, pi and 12 are really easy to locate because each scale mark is just pi and 12. So we've got 1, 2, 3, 4, 5 pi and 12. Minus 7 pi and 12 is easy to find. 1, 2, 3, 4, 5, 6, 7. Minus 7 pi and 12. So using the grid is really, really useful, and of course it's going to be that's going to be symmetrical there, it's going to be symmetrical there and there. You can almost tell just by using the grid what these values are going to be. So that there's 1, 2, 3, 4, that's 4 pi and 12. So it's fairly easy to see, but I'm going to go through the process of finding them anyway. So let's find the first maximum. The first maximum we find by looking at this expression here. Maximums for sine, the first maximum always occurs at pi and 2. That's for any sine graph. And that's being dilated by a factor of 2, and then it's being translated to the right by pi and 12. So that means we're going to add pi and 12 to it. So we multiply pi and 2 by half, add pi and 12, we get 4 pi and 12, which is pi and 3. But I said that before, didn't I, that we're going to get 4 pi and 12. The other maximum occurs not at pi and 3, but a period away. So remember at the very beginning I said that we have a period of pi. That means the maximums are pi units apart, there they are, and the minimums are pi units apart. So once we've got one maximum, we can find the other one just by adding and subtracting the period. So we get minus 8 pi and 12. In the same way, we can find the minimums. So there's our minimum. Our minimum for sine always occurs at 3 pi and 2. Dilation factor, translation, we get 5 pi and 6. And again, there's 5 pi and 6 there. We just need to count 10 units over because it's 10 pi and 12. And to find out the other one, we subtract, or we add pi. In this case, we subtract, and we get minus pi on 6, which is really 2 pi and 12, so 2 units across. And that's how we would sketch our graph if we were asked to also find the coordinates of the maximum and minimum. Okay, next question. Next question is a calculus question where we want to differentiate log e of x cubed plus 1. So we recognise that this is a chain rule. We let u equal x cubed plus 1. That makes y equal log of u. And if we differentiate that, we just get 1 over u. And if we differentiate u with respect to x, we get 3x squared. Write down what the chain rule means, du dx times dy du. Substitute those, we get 3x squared times 1 over u. Substitute for u, and we get 3x squared over x cubed plus 1. Now this expression here, or this question, question B, says hence. And that's a really important word. It means we must use our result. We do that ordinarily with these sorts of questions anyway, because this is an integration by recognition question. And what we do is we start with our answer. So we have differentiated log e x cubed plus 1 to get this. So if we integrate this expression, we'll get back to log e x cubed plus 1. And so that's the first thing we write down. We always write this start for integration by recognition questions. Integral sign, the answer to our previous question dx is the beginning of our question log e x cubed plus 1. And then we've got to muck around with this expression to see if we can get back to this, which is, as it turns out, not that simple. First thing I recognise is that we can take this 3 out. We know that with our integration properties, and divide both sides by 3. And then it's a bit hard to recognise this, but this is what we would do next. You've got to kind of recognise, or try to recognise, how does this look like this? Well, it doesn't, but if you divide the numerator by x squared and each value in the denominator by x squared, you're not really doing anything different, you're just multiplying by 1 in effect. You would then get this expression, which is x squared divided by x squared is 1, x cubed divided by x squared is x, 1 over x squared is x to the minus 2, and you can now see that this is looking very similar to that. All we need to do is make the 1 over to the power of negative 1, and that's the answer to that question. Let's go to the next one, which is question 8. So this question, it looks complicated. This whole idea here looks a bit complicated, but it's not really. Let me just go around there. And I'm going to apply 2 methods. One method doesn't even use this matrix equation at all. It just uses the idea that I'm transforming from this function to this one. And that's critical. So, first method. You see here, I'm transforming from this function to that one. Once you've got that understanding, you'll be okay. Normally, we would see questions transforming from this function to that one. And we would say, okay, I've gone from x squared to 3 times x, so I've dilated by a factor of a third, and I've gone left a third units. But we are transforming from this function to this one. So it's actually the opposite. My dilation factor is 3, not a third, because I'm going from this to this. And that's a critical point to understand. Similarly, I have a translation of a third plus a third, I'm not going left, I'm actually going right. I know it says plus third, but remember I'm not transforming from 1 over x squared to this function, I'm transforming the other way. So the translation is positive a third, and I'm going from plus 2 to nothing, which is going down by 2. So it's minus 2. Since I've got a dilation factor of 3, translation of a third and minus 2, I'll look at my expression here, which is really just saying the transformation matrix is transforming x and y with a dilation factor of a, translation of b from the y-axis, so the horizontal translation, here's the vertical translation. Since I've got that down here, I can just label what a, b and c are by using points. So my point xy is being transformed like this. Dilation factor of 3, translation of a third, and translation down of minus 2. So that'll give me the answer of a equals 3, b equals third, and c equals 2. Now I can take a matrix approach as well. Let's do that. So first thing I'm going to do with a matrix is actually I can just add x plus b, y plus c, and this t of x means that I'm transforming x and y to my, this is my pre-image, to my image. And so I can rewrite that as x dash y dash, not to be confused with derivatives, but this basically means that my x transformed. So that's going to be this 1 over x from this particular expression. So I've got my matrix, I'll just multiply a by x plus b and 0 by y plus c, and I get this expression here, or this matrix. So really, transformed x equals ax plus b, and the transformed y is y plus c. Now I am transforming from this expression up here to 1 over x squared. So what I would substitute into my transformed expression is my expressions for x and y. So I'll put my new value, my transformed y was really y plus c. And y plus c, well, I'll just take it one step further. Y is really g of x, and 1 plus a x plus b squared minus c is really all of this over here. So these values is what I'm going to be given to transform into 1 over x squared. So you can see that a is going to be 3, b is going to be a third, minus c is 2, so c is going to be minus 2.